Hello everyone, welcome back. In the last lesson, that is lesson number 10, we have discussed the working of and construction details of a moving coil galvanometer. Okay, today we will learn how you convert a moving coil galvanometer into an ammeter and a voltmeter. A moving coil galvanometer cannot be directly used for measuring currents because of two reasons. First reason, it has a very large resistance. It is a bulky instrument. It has high resistance. So it will affect the current in the main circuit. Second, it is a very sensitive instrument. You know, the hair spring in the moving coil galvanometer is very sensitive. The galvanometer gives very large deflection even for very negligible current of the order of microamperes. Because of these reasons, we cannot use moving coil galvanometer directly as an ammeter. But we can use it as an ammeter by making some modifications on it. Today, we are going to discuss the modification. Okay? A moving coil galvanometer can be converted into an ammeter by connecting a small resistance in parallel with it. This small resistance connected in parallel is known as shunt. We denote by the letter S. So how will you convert a moving coil galvanometer into an ammeter? By connecting a small resistance in parallel with it. Okay, this small resistance is called shunt. Let us do the equations for this. Conversion of a moving coil galvanometer into an ammeter. Conversion. Moving coil galvanometer into an ammeter. Okay. So I am drawing the galvanometer. This is a symbol of a galvanometer. Okay. I write this as G. Resistance of the galvanometer is written as G, capital G. Now, to convert it into an ammeter, we have to connect a small resistance. This is the small resistance in parallel. The small resistance I denote as S. This is known as shunt. Small resistance is known as shunt. Okay. So capital G is the resistance of the galvanometer. S is the shunt resistance. Suppose a main current I is entering the galvanometer. See, this galvanometer shunt together, it is known as ammeter. That is why I put in a dotted box. In the dotted box, galvanometer and shunt together, that is known as an ammeter. So, main current enters the ammeter. Since shunt is in parallel, you know, most of the current passes through the shunt only. A negligible amount pass through galvanometer because it has very high resistance. So I am taking current through the galvanometer as Ig. Remaining current, that is a very small fraction, that will go to the galvanometer. Now it comes out. See, while coming out, these two currents add up here. So major portion of the current passes through the shunt only because it has low resistance path. Only negligible current pass through the galvanometer. But when they come out of the ammeter, they combine. Total current remains the same. So current in the circuit is not affected. That is why we are using this small resistor. So this is an ammeter. So the shunt is connected parallel to the galvanometer. The voltage across the galvanometer will be same as voltage across the shunt. In parallel combination, voltage remains same. So voltage across galvanometer is, what is voltage across galvanometer? Current through the galvanometer is, see here one change I have to make. Current through the galvanometer is Ig. Okay, I have marked for this shunt. See, current through the galvanometer is Ig. Okay, current through the shunt is I minus Ig. So voltage across the galvanometer is Ig into resistance. This is the voltage across the galvanometer. Now I can find out, we have to find out voltage across the shunt. Equals current through the shunt is I minus Ig into resistance of the shunt. Okay. But in parallel combination, these two voltages are same. Parallel voltage remains constant. Therefore, we can write Ig into capital G equals I minus Ig into S. So you can find out the shunt resistance. Shunt is equal to Ig into G divided by I minus Ig. Here I is known as the main current and Ig current through the galvanometer. Okay, I minus Ig is the current through the shunt. So we can find out the value of this shunt if you know the range of the ammeter. Range of the ammeter is I, main current. Galvanometer resistance, if you know main current and galvanometer resistance, you can find out the shunt. Okay, this is how we convert a galvanometer into an ammeter. Okay, children, this is very important for numericals also. Now we can convert galvanometer into voltmeter. One more thing, the ideal ammeter means it should have zero resistance. Remember that. An ideal ammeter means what? Zero resistance. Ideal ammeter has zero resistance. And ammeter, always connected in series, right? In a circuit. Now, conversion of how to convert galvanometer into voltmeter. See, a galvanometer can be converted into a voltmeter by connecting a high resistance in series with it. So, this is a galvanometer. Resistance is G. You connect a high resistance in series with it. So this arrangement become what? Voltmeter. See this together, galvanometer plus high resistance together. That is why I am putting in dotted box. This is voltmeter. Suppose voltage across the voltmeter is V. Okay. And current through the galvanometer, Ig. You know, current through the galvanometer same as current through the resistance. Series connection. So we can write here V is equal to current into resistance. Current is I, resistance is R plus G. So V by Ig is R plus G. So you can find out R, V by Ig minus G. So this is the equation to find out the resistance that has to be connected in series to convert a galvanometer into a voltmeter. And a voltmeter, ideal voltmeter means it should have high infinite resistance. An ideal ammeter has zero resistance and an ideal voltmeter has infinite resistance. Okay, this is very important for the theory part as well as numerical problems. Okay, everyone. Thank you for watching.